Good day everyone, this is Professor Friday coming at you one more time. In this video we're going to be solving a system of differential equations. It's already going to be listed for us in sort of the standard form that we look for if we're going to be using systematic elimination, which is where we have all of the x's lined up, and in terms of the polynomial differential operators, we have all the y's lined up in terms of their polynomial differential operators, and we have the non-homogeneous portions over on the right-hand side of the equation. So everything is basically set up as we would predict it to do. So, with that in mind, first decision that we get to make, if we are going to solve this system of differential equations using using an elimination, we get to make a decision about whether we'd like to eliminate the x variable or eliminate the y variable. Now, that elimination also helps us decide which one of these functions we're going to be solving for first. Now, with that in mind, out of all of these variables that are listed up here, the one that stands out to me the most is the 3x. The reason that that stands out to me the most is due to the fact that there is no differential operator on it. So if I want to solve for x at the end of the problem, quite literally all I would need to do is plug in a value for y, evaluate d plus 2 of that function, move it to the other side, and divide both sides by 3. That'll give us algebra to do rather than the solution of a differential equation. So because of that, I am going to make the following decision. I would like to eliminate x first to solve for y. Now, keeping in mind that y is going to be a function, we're going to plug that back in after the fact and solve for x. Now, does it have to be done this way? Absolutely not. If you prefer to solve for y as a differential equation rather than solving for x using algebra, that's your mistake to go ahead and make. So you feel free to go ahead and do that. Now, one of the keys to elimination, if we are going to eliminate x first, is we need to make sure that the coefficients of x are the same, but also with opposite signs. So what we're going to do is multiply both sides of the equation by the appropriate polynomial differential operator. So for the second equation, I see that we will need a d plus 1 associated with this. And I see for the first equation that we'll need a 3 associated with this. Now, by my calculation, that's going to give us a d squared in the second one, and then some sort of 3d in the first one, as far as the new coefficient for y is concerned. Because I want to make sure that the coefficient of y stays positive, I'm going to multiply the first equation by negative 3. So what we will wind up with is negative 3 times d plus 1 x minus 3 times d minus 1 y is equal to negative 3 times 2. For the second equation, that'll be 3 times d plus 1 times x plus d plus 1 times d plus 2 for y. That'll be equal to d plus 1 applied to negative 1. D plus 1 applied to negative 1 means that we'll be taking the derivative with respect to t of 1 plus 1 times negative 1. So that represents d plus 1 applied to negative 1. Now, the astute observer will notice that that simply means negative 1. Then we're going to add these two equations together. So we notice over here the x variable gets eliminated. In years past I used to make an MXC reference to that, but kids these days have no idea what the most extreme elimination challenge is. So in the meantime, y'all can get off my lawn. What we will wind up with, however, is the following coefficient of y: d plus 1 times d plus 2 minus 3 times the quantity d plus 1. Over on the right-hand side, we'll have a negative 6 and a negative 1 added together. That'll be negative 7. So, feeling pretty good so far. Next up, I would like to do a little bit of algebra on the inside of these parentheses here. Maybe expand, combine some like terms, you know, the usual. So, we got d squared plus 3d plus 2 from that FOIL. Distribute the negative 3, we'll have negative 3d plus 3. Neato. So put that all together, and the new polynomial differential operator applied to y is, I believe, d squared plus 5. So we got ourselves d squared plus 5 times y is negative 7. So once we're in this form, we have a couple things to do still. One of them is the associated homogeneous equation. Thankfully, we've already got it in the appropriate form. This is d squared plus 5 times y is equal to 0 for the associated homogeneous equation. The d squared plus 5 squared we get to treat in a very fun way. Because 5 isn't a perfect square, we have to force it to be a square against its will. So that'll be d squared plus the square root of 5 squared. So the two linearly independent solutions that we're going to come up with will be the cosine of root 5 times t and the sine of root 5 times t. Now, I'm going to wave my hands at this a bit. Rather than trying to do annihilators or something, what I'm going to do is apply the superposition principle and say that because we have a constant over here and the constant is not part of the complementary solution, we can assume that our particular solution is going to be a constant as well. Now, if we do make the assumption that the particular solution, if we make the assumption that this is going to be a constant, we'll use a naught for that. The second derivative of that constant will simply be 0, and what we'll wind up with is the fact that 5 times a naught is equal to negative 7. So your particular solution is going to be negative 7/5. When we put those two things together, the complementary solution as well as the particular solution, complementary solution plus particular solution. For the complementary solution, that would be c1 times the cosine of the square root of 5 t plus c2 times the sine of the square root of 5 times t minus 7/5. That's what we'll get for our y. Now that is of course only half of the battle due to the fact that we still need to solve for the x variable. So what I'm going to do is head back to the original system of equations and point out once again that we started this whole process with the intent of plugging this y in here so that we can use just algebra to solve for x. So what I'm going to do is recopy this differential equation, and we'll point out that we are going to plug back into 3x plus d plus 2 y is equal to negative 1. What I'm going to do is actually do a little bit of algebra here. Let's say that this means that 3x plus y prime plus 2y is equal to negative 1, and some more algebra. X is equal to negative 1/3 minus 1/3 y prime plus, oh no wait, minus. Algebra is hard. Minus 2/3 y. Yes, that is much better. Alright, so at this point, this will be negative 1/3 minus 1/3 times y prime. So I'm going to grab the expression that I just got for y from our bottom of the first page right here. I'm going to go ahead and differentiate that thing. So the cosine will become a negative sine. We'll get an extra factor of the square root of 5 from the chain rule. Sine will become positive cosine. We'll get an extra square root of 5 from the chain rule. So that'll be negative square root of 5 c1 sine of square root of 5 times t plus square root of 5 times c2 times the cosine of the square root of 5 t, and then the minus 7/5 that we had at the end of it is no longer around because that is a constant. Minus 2/3 of, let's go ahead and plug in the original y function that we have, which is this little guy right here. Minus 7/5. Alright. So it looks like we're going to wind up having three different kinds of terms. We're going to have sine of the square root of 5 times t terms. We're going to have cosine of the square root of 5 times t terms, and we do have a couple of constants in here as well. I would like to group appropriately. So for x, we will get, let's group all of the sine of square root of 5 times t terms together. Sine of the square root of 5 times t. So up here I see positive root 5 over 3 times c1. Root 5 over 3 times c1. That's exciting. And we'll have a minus 2/3 c2 from the second part. Minus 2/3 c2. Groovy. Plus, let's group all the cosines together and do something similar. Cosine of the square root of 5 times t. All right, so up here, looks like we'll have a negative 1/3 times positive root 5 times c2. So we'll call that negative square root of 5 over 3 c2. And then down here we'll have a minus 2/3 c1. Notice how similar these two things are. They sort of have a nice little duality going on. That's not a coincidence. It's also not a coincidence that whatever complementary solutions we got for y, we're getting the same complementary solutions for x. That tends to happen in our systems of equations. We also have a minus 1/3, minus 2/3 of negative 7/5. Looks like a great reason to establish a common denominator. Do 5 over 5. So here we'll have negative 5, and here we'll have positive 14 for positive 14 over 15. No, wait, hang on. Negative 5 plus 14, that's 9. 9 over 15, that's like 3/5. You know what? I'm writing it up here, because that'll be prettier. I don't even know why I crossed that stuff out. That just seems rude of me now. So final answer for this one is we have both an x and a y in terms of t. If your solution doesn't look exactly like this solution because you made the decision to solve for, say, x first and then solve for y, that's okay. It's really okay. There's an explanation for where all of these coefficients come from, but essentially in terms of c1 and c2, all of these coefficients obey the Pythagorean identity. So this 1 squared and this 1 squared are really the same as root 5 over 3 squared plus negative 2/3 squared, and it's the same as negative root 5 over 3 squared plus negative 2/3 squared. So more explanation on that when I feel like it, but Jurassic World is on the TV and I'm really enjoying it. So I'll do another video a little later on. Okay, bye!